So I'm going to introduce a new activity. This is a small hydrogeophysics activity that kind of stems out of some of the work we've been doing in the groundwater geoscience program over the last few years, most recently in the archetypal aquifers that Lisa went over this morning. Project members are myself and most of the near surface geophysics section in Ottawa. Collaborators are the Rideau Valley Conservation Authority, the City of Ottawa, and the Ottawa River Keeper. On the left here, we have a map of highly vulnerable aquifers in the Ottawa area. These aquifers are highly vulnerable either because they have very little overburden or because they have a thick sequence of highly permeable overburden. And so what that means is any contaminants introduced at the surface can make their way relatively quickly to the aquifer, or if not to the aquifer, right into the ecosystem. So being in an urban environment, there's a lot of stress on these aquifers, and one of the main stresses is chloride. It's been observed that chloride concentrations are increasing in Ontario's waters. Here on the far right, we have a map from the Provincial Groundwater Monitoring Network data. And in the middle, we have a map from surface water samples collected by the Ottawa River Keeper. And anything in red there exhibits concentrations that have acute toxicity, so greater than 640 milligrams per liter chloride. And anything in yellow and orange is chronic toxicity, so greater than 120 milligrams per liter chloride. So these measurements tell us that we might have a concern about contamination here, chloride contamination, but they don't tell the whole story. In particular, it's observed that in the surface water data, when you take the source of contamination away, so de-icing salts, the concentrations don't go down. So the concentrations remain in the surface water. So we have some kind of storage going on in the watershed, in the stream aquifer system. And we think that one of the ways to help understand that system better and some of the storage mechanisms is by using geophysical methods. So this is an example of geophysical monitoring of a simulated pump and capture experiment. Now this is in an alluvial aquifer where geophysical electrical instrumentation was put down boreholes. And what we're able to do is image the contaminant distribution in space. And also we're able to get estimates of the mass in the system over time and also the mass that was pulled out of the system. So essentially we can judge the effectiveness of the remediation. We can also get estimates of where the remediations failed and where there may be leftover mass in the system. This is another example data set from the Ottawa area. This was collected over an agricultural stream on the flanks of an esker aquifer. And the data shows some interesting patterns in terms of the electrical signature of the subsurface, both in terms of the near stream patterns and also patterns in the aquiclude that are protecting the esker aquifer. However, this data set really doesn't give us all the information that we need to understand the fluxes in the system, what's going in and out of the stream, what's going through the aquiclude into the aquifer. We really don't know. So the main objective of this program is really to design an experiment that has a three-dimensional distribution to capture the heterogeneity, and also has all the supporting data that we might need to better understand the fluxes in the system. So this is a totally new project. So the first step is site identification. So we're working with our partners to identify potential urban stream targets in the City of Ottawa, in the Rideau Valley Conservation Authority. Then we'll have preliminary data collection just to characterize those potential sites a little better. And then we'll have instrumentation of the site. And the idea is that the monitoring phase for this project will last about 2 years. And that's so we can really get an understanding of sort of the seasonal and anti-seasonal dynamics. We have some anticipated complications, one of which is limited base flow and recharge. The extreme example of that would be an engineered stream bed with a highly permeable urban setting. In that case, the stream would mostly be storm response. We have short and variable time scales. We have things going on the order of days, but we also have seasonal dynamics. So we want to be able to capture and analyze those different time scales. We have fractured bedrock aquifers, so the heterogeneity associated with that. And then when we have all of the fun stuff that goes along with geophysical imaging. Yeah, if you have any comments or you'd like to talk, there's my contact information and some questions.